Bill, you copy me?
Well, good morning.
Good morning. I guess my computer's working all right.
Yes, I think so. I'm just getting a little organized myself here. That's better.
Yeah, I guess Jesus came on.
Yes, we're just getting organized still.
Buenos dias, Jesus.
There we go. I did receive an email this morning from Jesus who informed me that we may have a couple of other participants this morning.
Yeah, I saw somebody there. I didn't recognize who he was, though.
Yeah.
Rodriguez or Carlos Rodriguez.
Good morning, everyone. Can you hear me?
Yeah.
Yes, your audio sounds a little extra loud.
Oh, okay. It's better now?
Yes, you could even a little bit lower would be okay.
Okay, I hope it's better now.
Yes, that's great.
Okay.
Yes, so are we expecting one more participant, two more participants?
Yes, I'm. We are waiting for Brian and two more students here, but maybe we can start our meeting and then they can incorporate later. Mhm.
Okay,
Mm.
no problem.
Mm.
I did receive one email from you, Jesus, about previous recordings of the meetings. Um, I don't know if you had a chance to look at what I uploaded, but there were quite a few meetings that were not on the YouTube site, but which I did have recorded locally, and so I added those to the collection. But I did not did not really make any attempt to put any of the metadata or the the titles and so forth. Uh, so that still probably needs to be done.
Yes, Professor Page, thank you very much for your work because it's a huge work. Uh, yeah, and I have not finished to review all, but it looks too nice now.
Okay,
Thank
that's
you
good.
very
I
much. Yeah.
unlike my original intention, like almost 2 years ago now, I started out by trying to make sure that we only had online that part of the meeting that was, you know, starting from the presentation and then ending at the end of the presentation. But of course, every meeting starts with a little bit of discussion of something else, and um, so so I haven't done any editing at all. Like I haven't tried to trim it. So it after a while, I guess it even doing this every 3 weeks, it seems to catch up on me, and I don't quite dedicate enough time to doing the organization part of it.
Mm.
But at
Then,
least we do have the recordings.
yes, I think that the organization by years helps too much to
Ah,
review
okay,
the subjects, and then and it is pretty nice now.
okay.
Yeah.
Well, that's good. I'll try to keep more current to make sure I don't let these things slide and
Mm.
do it within a day or two after a meeting. Uh,
Okay.
Only one other sort of point is that uh, now we have this new technology called AI that seems to be occurring, like incorporating in a lot of different places. And so Zoom does have something they call AI Companion, which is uh, if you're using a current like an up-to-date version of the Zoom software, you would probably see a notice when the meeting starts saying that AI companion option is enabled. Uh, this this AI thing does a reasonable job, I think. Not a great or a perfect job, but it does a reasonable job of trying to summarize the content of the meeting. It's based on transcripts that it generates as we have our meeting, and it tries to summarize what we're saying. Um, there are a lot of times when say people's names and so forth are misinterpreted. But other than that, I in my first experiments with it seemed fairly successful. So I was intending to make these summaries available online as well. I'm not sure if you have had a chance to look at those. I think I did send a link.
In fact, Zoom sent to all the participants automatically. Uh,
Ah,
then I had the opportunity to read that summarize, and I think it is not so bad. And, this reflects some of the ideas of the meeting. Maybe we need to modify or correct some of them. But
Yeah.
I think that it is too much. It's good because we have a summarized of the discussion there, and maybe we can use later for working more some ideas and something like
Mhm.
this.
Or to go back and try to, say, well, what were we thinking 6 months ago? Sometimes it's not so easy unless you have some kind of written summary. And so even though it's imperfect, I also have the feeling that it might be useful and it may get better,
Yeah,
as
that's
time goes on.
probably it'll get better.
Well, it, at this point, I'm still a little skeptical of AI, um, but it is impressive every once in a while, so it's something that's doesn't cost us any extra to use, and as long as you both agree that it might be something
I think
that'll
I asked it about a trig identity once and it got it completely wrong, but it says it with conviction.
yes. So I think we're getting used to the fact that we might may or may not get a useful answer, like but at least it's an answer. So and sometimes just having a possible answer and chasing down the whether it's actually true or not is helpful in getting you to another
You have to
source of
think about it
information.
yourself. What is this? Is this right?
Yeah, so you take a few minutes to think about it, but in the meantime, you learn something else. So
That's pretty
maybe it's
funny,
okay.
actually.
Yeah. Okay. Well, then we'll continue. I wasn't sure if the participants were always getting a notification that this was available. The other thing that they do provide is that the chat, if you enable it, I think, then the chat function um, that's part of Zoom allows you to chat with the AI companion. So you can ask it, like if you're joining the meeting a bit later, you can ask the AI for a summary of what people have said so far. Um, it, and you can actually ask it questions about during the meeting about what someone said. So it's I haven't had much chance to play with that, but in a larger meeting, I think it might be useful. All right. So today, I think our general conclusion was that uh, Dr. Sobczyk would be presenting. Uh, Mostly on the subject that was, I think you sent around a paper, an updated copy of a paper, Dr. Sobczyk, last week, was it? Um,
Basically, uh, I have basically the talk I gave, which of course Dr. Cruz had already listened to, but we can. Uh, that's basically what I have. I've had a hard time getting started back on this side. My flights were delayed for a whole week, which was kind of disconcerting. It was canceled every day for a whole week, so it was pretty awful getting back here. But I did finally make it back. That volcano is just continuously spreading ash all over the place.
ah, so that's the reason for the cancellation is the volcano.
Yeah, that's the reason they gave. There's probably other reasons as well, but that's the reason. Since other planes were flying in there, but somehow United Airlines didn't want to risk their planes, or who knows the reasons for it.
Oh, wow. Okay. Uh, sure. So if you're willing
Yeah,
to.
I can start with it, and then maybe Dr. Cruz will have something to say. He's been working on some of the same ideas as far as whether this new idea of a duality can be appropriated or used in category theory.
Hmm.
So
I'm the idea of this duality is still, for me, the most sort of controversial part of it, I suppose, is the notion of global versus local duality. It still can't quite get my head around.
okay, so maybe I'll just start with, I think I have got those definitions down pretty well in the talk. In fact, I've been working a little bit with Dr. Havel, and I think he's starting to use it now for his work on the generalization of Heron's formula for the trapezoid. So it's pretty interesting that I think he's actually, we're talking about writing a joint paper on some of his ideas, incorporating duality. So I have one, I can show one thing about that too that I talked about. So
is that concerning projective geometry? Is that...
Yeah, it's close to graph theory, really. The ideas, but I'll mention it, and I can show you what I have about that. So
Okay.
if you want, I can share screen and we can go to it.
Sure.
Okay. Let's see if I can get it up there right. Okay, can you see that all right?
Yes,
Oops.
it looks good to me.
Yes, we can see.
Okay, it looks like it's all right. Okay, so that's exactly what I wanted to talk about, is local duality and what I call null cone geometry. So we'll just go on. So I started my talk with discussion of the Pauli matrices, which of course we don't have to spend any time on since everyone's familiar. I was talking mostly to students, so I thought I would start with talking about Pauli matrices. And I gave this talk at Universidad de las Americas on January 26th. So what, a few weeks ago now. Okay, so I started by talking about these so-called Pauli matrices, which we're all familiar with. In particular, can be used to define, well, I consider these to be the coordinate matrices of the geometric algebra of space, G3. And of course, as coordinate matrices, we're talking about three vectors which have square one and which anti-commute. So that's the rules that basically abstract the properties of the coordinate matrices, which are the coordinates of these vectors in a basis then. So, okay, the matrix of E1 then is sigma 1, sigma 2, and sigma 3. So I'm not going to spend time on that since we're all very familiar with that. Okay, but I point out this isomorphic geometric algebra 1, 2. So what is the geometric algebra 1, 2? Well, it's a geometric algebra generated by three vectors, E1, F1, and F2, where E1 squared is equal to 1, F1 squared equal to F2 squared equal to -1. And if we define the trivector J equal to E1, F1, F2, then you can calculate that if you take the multiplication of these three vectors, E1 times E2 times E3, and you square that, that's exactly what you get when you take E1, F1, F2 squared, and you get -1. And the pseudoscalar element of both these pseudoscalars, I, which is E1 times E2 times E3, defined up here, are in the center of the algebra. So they commute with all the elements in the algebra, as we're all familiar with. Okay, so now I'll talk about geometric algebra G1, 2 of the null cone. And I use the notation N1, 2, and 3. So I'm looking at 3 null vectors, anti-commuting null vectors, which I'm denoting here by A1, A2, and A3. So that means they all have square 0, and they all anti-commute. So AI times AJ is equal to minus AJ times AI. And of course, they define a Grossman algebra consisting of 0. Well, any of these vectors have square 0. And of course, we take A1, A2, A3. Then we have the bivectors, A1, 2, A1, 3, A2, 3. Then we have the pseudoscalar. Well, the trivector, A1, 2, 3. Now, okay, so think about a null vector as being an oriented direction or array. Well, the best way to think about that for physics students or physicists as a direction on the light cone. Okay, all the directions on the light cone or rays on the right cone have square 0.
Can I make one comment or one question?
Okay.
It does seem unusual when you write span there that you include 0 as an element of the.
Yeah. Well, yeah, that is a little bit strange, but actually it is over the real numbers. We can take 2A1 plus 3A2 and so on, but I'm more or less emphasizing with the 0 that A1 squared is 0. And of course, A1 times A2, since they're anti-commutative, all the bivector squares are 0 as well. So all these quantities, A1, A2, A3, the bivectors and the trivectors have square 0 because, well, the AIs anti-commute, and of course, so it makes it, if you square A1, 2, you're going to get all the elements have square 0 as well. But it is over the real numbers, so I do denote this over the real numbers. But well, if I could put 1 there, but well, yeah, you could put 1 there instead. I was a little bit reluctant to use 0, but I'm just emphasizing that all these quantities here that you see have square 0. So there's no metric involved because to define a metric, you'd have to have a inner product. Well, you'd have to have an inner product, non-trivial inner product. And the inner product, if you think about an inner product, they all have 0. And of course, it's well known in the Clifford algebra. If you take the trivial quadratic form, namely the quadratic form 0 itself, then it's really a Grossman algebra. Or
It's sort of implicit in most cases that we include the identity.
okay, so yeah, we
all.
could replace that with 1 there. It's okay. But,
And then, but then you perhaps have another question like, why do you include 1 element whose square is not 0?
well, that was the idea.
Yeah,
But of
I
course,
understand.
I do put R here, so we are over the real numbers, so we can
But in
multiply.
that sense, 0 or 1 does generate 0 as well. Like that's.
Yeah, that's true. So maybe I should also. I wanted to have 2 to the 3 elements. There's 8 elements here: 1, 2, 3, 4, 5, 6, 7, 8. So I could, if I just left it off altogether, then we only have 7 elements. So well, yeah, I guess I should put 1 there. It's a little confusing for people to put 0 maybe there.
Okay.
Okay. So a null vector is an oriented direction or ray, but again, it has square 0. So okay, and now we define. Now I'm just pointing out the how we can get the isomorphic geometric algebra G12 simply by multiplying, take E1 and take minus I E2 times I times E3. Well, remember that I is in the center of the algebra. So now we're just considering this to be F1 and this to be F2. We can change the signature of the geometric algebra simply by multiplying E2 by I and E3 by I. And of course, that's my definition of J here then. So you can see really they're identical. It's just that we're interpreting minus I times E2 to be F1, considering that to be a single quantity, changing the signature of the geometric algebra. So that's always confusing. There's so many isomorphic geometric algebras that also becomes, and that's the thing, by introducing null vectors, we're defining exactly what we mean by a vector at the beginning. So a vector, a null vector is a vector. Well, you can see in the geometric, in the Grossman algebra N3R, it's spanned by 3 null vectors. And of course, then you have the bivectors and you have the single trivector. So they're defining in a metric free way what we mean by, it's abstracting the concept of direction independent of a metric. Okay, so here we have F1.
Just, I know this is still sort of an elementary concept, but what's called a bivector in one case is a vector in another case. So
well, that's what happens when you have all these isomorphic geometric algebras. That's right. The algebra G12 is isomorphic to G3, but I think the basic geometric algebras are these that have signature 1, comma n, and then we define all the other quantities are in terms of null vectors. I believe that the concept of a null vector is really very basic. It should be recognized as a basic concept because it abstracts the notion of direction alone. No metric, no length or anything like that, just the idea of a direction.
But the notion of a bivector generally doesn't involve a direction as such, but rather an orientation. Well, how should I say that? If you think about the sort of geometric model for a bivector, you think of rotation in a plane, right? So
well, Grossman, swept out. So A1's wedge A2 it sweeps out the vector A1 along the vector A2, and that's what generates the idea of a plane segment. I think bivector is plane segment, trivector is a volume. Well, I say volume, but it abstracts just the notion of a 3-dimensional space without any concept of distance involved or volume.
But it's a bit disorienting to say that you have an isomorphism, but this isomorphism is mapping a vector into a bivector, because geometrically speaking, the vector is something you would call a direction, but a bivector is not. A bivector is something you would call a rotation or something like that.
Well, I'd call it a plane segment, a direction of a plane. Okay, you're thinking about Grossman's idea of sweeping one vector, one direction out along another. Of course, if you sweep a vector out along itself, it doesn't do anything. Okay, you can, it doesn't matter. Array is just an infinite line segment going off to infinity, or in the direction of a light of a photon, for example, on the light cone. So, well, that's why I call it a null vector is an oriented direction or ray. A ray being a direction. Point your finger in a direction, that's the direction of a ray. Independent of the concept of a line segment. Well, independent of the concept of a Euclidean concept or Lorentz. So I take a null vector to just abstract the direction of a ray, just the direction in space. Point your finger in any direction. That's
So
what a null vector represents.
another way to sort of express like, okay, so maybe the thing is that when you talk about direction, you're talking about the direction in this higher dimensional space, like this. You're not talking about a direction in three-dimensional space. You're talking about the direction in this eight-dimensional space.
Well, for example, if you just take one null vector, A1, for example, it represents, you can think about it as representing a direction. We call it a null vector. Vectors represent directions, okay? A bivector represents, well, I take it as a product of two null vectors, AI times AJ. Well, anti-commutative equals minus AJ times AI, as we have written down here. That's a bivector, so that's a direction of a plane and of a two-dimensional space, three vectors, four vectors. And of course, if you take a Fourier series, you're in infinite number of dimensions if you want to think about in an infinite dimensional space, sines and cosines and whatever. Okay, Grossman algebra, okay. So, but here, okay, in this definition here, you see here we're saying minus IE2 is a single quantity. So we're still taking this geometric algebra E1 minus IE2 times I times E3 over the real numbers. So these are what we're calling vectors now. Well, you can see, well, then we have to talk about what we mean by imaginary Euclidean, well, imaginary E2. Well, of course, there's all kinds of things like that we have to deal with. Okay, well, here, so if you want a matrix representation of F1, we can just write it as E1 times E3. And so F1 has a matrix, the coordinate matrix of the vector F1, which has square minus 1, is 0, 0, 1, minus 1. And F2, we can say it's E1 times E2. And if you just take the matrices, the usual Pauli matrices, and multiply it, you get J and minus J is representing the vector, which has square minus 1, the coordinate 2 by 2 matrix of that. Okay, now I introduced a geometric product of UV and vectors in 1, 3 or in 1, 1, 2. So that's the usual geometric product, Clifford product, breaking it into symmetric and antisymmetric parts. We call the inner product the symmetric part, the outer product the wedge product. Okay, okay, now I want to introduce the null cone generated by three null vectors, C1, C2, and C3, 1, comma 2. Okay, but now we define E1 equal to C1 plus C2, F1 equal to C1 minus C2, and F2 equal to minus C1 plus C2 plus C3. And okay, and if we just turn this around, another way of saying the same thing is we're defining the null vector C1 equal to 1/2 E1 plus F1. Okay, so that's C1, C2, and C3 as null vectors. Okay, well, here I have a picture of, if you just take one null vector, which has square 0, C1 squared is equal to 0, it defines a direction, say, of R1. Okay, you can have C1, 2 times C1, and so on. And of course, all multiples of C1 squared is equal to 0. Now, okay, so if you take one null vector, C1, now if you take R2, you can define it in terms of C1 and C2 along a two-dimensional light cone. And then if you take the sum, C1 plus C2, you get E1. That's just like gamma 0 as a null vector in the Dirac algebra. And C1 minus C2 is F1. That's the vector it has square minus 1. Okay, now if we take a third vector, so in this picture, this is C1, C2, and C3, then you can think about them as being on a sphere here with 120 degrees between each of these three vectors here. So we have three rays. The light cone is this cone here that you see, and of course, that's the 0 point. It's undefined. And then, of course, the negative light cone is going in the opposite direction then.
Some
Well,
nice
okay.
graphics. Very, very nice graphics.
Okay, well, I struggle with it.
No, it's much very clear compared. Like I think it's.
Okay, well, thank you. So anyway, you can see I try to make it more or less 120 degrees. And okay, so that's the light cone then. And then I'm just showing the usual properties of a parabola, ellipse, circle. The most interesting thing here is if you take these plane segments to the origin, it defines a pair of lines. Then, well, you can see a line going off this way and crossed lines. If you take it along the edge of the parabola, you get a single line going to the origin. If you take it straight down, you get a two-dimensional light cone. But of course, you can have it at any other angle as well, crossed lines. It defines a parallel lines and a couple of lines on the light cone then with different angles. If you move it back this way, you get a single line at the end then. But usually, of course, people only talk about parabolas, ellipses, these circles, but this idea of lines, when you take the plane going to the origin, a single line, if it's tangent to the null cone, and you get a pair of lines if it's at any other angle, then this is a vertical plane, of course, here. Okay, so again, this is our multiplication table. And I claim that this multiplication table, in a certain sense, is a local definition of the product of two matrices. It completely characterizes matrix multiplication in terms of the product of any two of these null vectors, C1 and C2 in this case, the simplest case. So multiplication of null vectors, C1, C2 times C3, well, that defines the geometric algebra G12, inner product. Okay, now you see, so at this point, this is where I'm introducing an inner product, and I'm saying that I'm defining the inner product of Ci dot Cj equal to, well, 2 times the inner product equal to 1. And that's what gives us the metric 1, 2. Otherwise, we're just dealing with a Grossman algebra, no metric. And the outer product, of course, is the wedge product. C2 Ci wedge Cj is equal to Ci Cj minus Cj Ci. And again, you have the geometric product as the dot product and the wedge product together. Well, here I'm just playing with the geometry a little bit. I define a unit vector r hat theta by taking cosine theta C1 plus sine theta C2 divided by the square root of cosine theta sine theta. And if you simplify that, you get 1 over tangent theta C1 plus tangent theta of C2. And if we define the conjugate of that, well, I'm just changing the sign here. We have cosine theta C1 minus sine theta C2 divided by that. Well, you can square these out, and you can see when you square it out, you get 2 times tangent theta times 1 over tangent theta. times C1 dot C2. Well, C1 dot C2 is 1/2. So you see that is a unit vector then. And this one is a unit vector which has square -1 because minus 2 C1 dot C2 times tangent theta times 1 over tangent theta. So that's -1. Well, I do some calculations with this, just experimenting with it. It's interesting that this idea of taking 1 over the square root of tangent theta as reciprocals plays an important part in various in one of my earlier papers. You can define what was I doing in that paper? I was oh yeah, finding when you look for the root of a cubic equation, you can actually find the cubic equation by considering such quantities: 1 over tangent theta, 1 over the square root of tangent theta, square root of tangent. They're reciprocals in two vectors which have, but I won't talk about that here, but some of the ideas are related. Well, okay, so I calculate the product of these things. You get all kinds of trig identities, which you have to be careful about. So, okay, so this, just experimenting again. If I multiply C1 times R hat theta times C1, project it onto the C1, the ray C1 times tangent theta. If I multiply by C2, then it multiplies it onto the other side of the light cone. Okay, well, but for example, if I take these other transformations, I take C1 plus C2 times R hat theta times C1 plus C2, we get this expression. Well, basically what you see we're doing, we're moving from one quadrant of the hyperbolic plane to another one. We get tangent C1, 1 over tangent C2, minus, plus, plus, minus, minus, minus. So we're basically, by using these transformations, of course, if you remember, C1 plus C2 is E1. This is E1 times E1 times the conjugate unit vector. And this is, of course, E1 here and F1 here on this side. But you can see we can move from one branch of the hyperbolic plane, which has 4 branches, or which is, instead of using Cartesian coordinates, we're using the hyperbolic coordinates of 4 quadrants, hyperbolic quadrants. Well, okay, I look at the orthogonality of these hyperbolic vectors. They all have inner products 0 for these definitions here, just to the outer products. But I won't spend too much time on that. Well, okay, so here's again picture of the light cone. You can think about this as being the hyperbola which goes to E1, and on this side, of course, we can take the hyperbola which goes like this. I didn't draw it in here. So if you're thinking about the Dirac algebra, you think about E1 as being gamma 0, and then we have each rest frame corresponds to, well, I'll talk about that a little later, so I won't talk about it here then. Here I'm trying to indicate that you can pick any of these unit vectors for our E1 can be any vector in the positive light cone here, any unit vector in the positive light cone, defined by 2 rays which cross at the origin here. Okay, so now for this is, I think, an important property here. So we're just looking at the algebra, the geometric algebra G1, 2. So again, that's E1 squared is equal to 1, F1 squared equal to F2 squared is equal to -1. Okay, so we have three C's, C1, C2, and C3. Now the interesting thing, if you multiply C1 minus C2 times C3 times C1 minus C2, and you carry out the operations, which are not difficult, you find that okay, because C3 is different than C1 and C2, we just get back C3. It doesn't change anything. Well, that becomes important for the next calculation. I'm going to show you the relationship. And okay, but now look at this. In this case, I choose C1 to be, well, I want to generalize that. You see, this can be Ci, Cj, Ck, any three vectors, but I'm just looking at it in the simplest case of the geometric algebra 1, 2, because, you know, any three of the C's completely symmetric, because remember, C1 dot C2 is equal to 1/2, or Ci dot Cj is equal to 1/2, no matter what two vectors in the geometric algebra you're talking about. So here I'm just saying that if you take C3 and you multiply it by C1 minus C2 on either side, that's a two-sided with F1 and F1 here, and you'll see it does not change C3, it leaves it invariant. On the other hand, if you choose C1 to be the same C1 here, you'll see it flips it. It flips C1 into C2. Again, it's just a simple calculation, which you can go through to see that. If you take C1 minus C2 times C2, C1 minus C2, you'll find that it flips it back to C1 then. Okay, and because of that property, that's why I want to define the permutation group Sn. So now let's take n of these Ci's. So if you take n of these Ci's, it defines the geometric algebra G1 n minus 1. So we looked at the case where n was equal to 3. Okay, for the case n equal to 3, that's the case we discussed up here. But now we just take n of these things, C1 up to Cn, for n greater than or equal to 2. And we define the transformation as where we're flipping. Okay, normally we take Cn just equal to C1, C2 up to Cn. But when I want to find the permutation where Ci goes to Cj and Cj goes to Ci, I call that Sn I comma j. So, okay, so the notation is this is C1 up to Ci, up to Cj, up to Cn, where I is less than j. But now you see I want to define Snji, where it reverses that, where j is larger than I. Well, I make this, so in this case, Snij keeps the order, the natural order, 1 up to Ci, up to Cj, up to Cn. When I is less, we don't change the order here, but we define Snji when j is larger than I. That actually just flips the vectors Ci and Cj and leaves all the rest of the vectors the same. So where only Ci and Cj are interchanged, leaving the other terms unaffected. Okay, now because we have this property here, what I can do is I can see that if we consider I less than j, and I might multiply Ci minus Cj Sn times Ij Ci minus, that will flip j and I in this. So it's really defining the permutation group. So this transformation, Ci minus Cj times Sn Ij Ci minus Cj, that just permutes the two vectors in the product. Now, if you examine that product, it's very complicated because remember, you have both the inner and the outer product. So you expand those terms, it becomes a big mess. But this allows you to commute any two terms simply by multiplying, in this case, be Ci minus Cj, ij. Well, that's just Sn, really. Ci minus Cj, it flips j and I, but leaving all the rest of the terms without changing. Well, of course, that defines the permutation group. So the permutation group is acting on this multivector C1 up to Cn. Sn is equal to C1 up to Cn, the product of all those, which is, if you expand that out, is a very complicated expression. Okay, well, again, here we take 3 points on the null cone, as you can see in this picture here. Okay, well, I was going to show you how this Heron's formula on the null cone can be defined. So remember, Ci plus Cj squared is just, again, these are null vectors, so you have 2 Ci dot Cj. But now you see, I'm defining C1 plus C2 squared equal to the distance. Okay, there it is. So the distance between C1 and C2, I call row 3. Okay, this is row 3. The distance between C2 and C3 is row 1. So now instead of defining, before I would just take this equal to 1, okay? But now I'm saying you don't really have to define the inner product of these things all equal to 1/2. You could just define it equal to the length of the size of this triangle here. So in other words, we could have defined the CIs in terms of any inner products, any positive inner products. We'll define the same geometric algebra, C1 comma n, or n minus, well, as we defined it earlier. So you don't really have to define all the inner products equal to 1/2. Of course, when you do that, then, for example, you can represent the permutation group simply by taking the double product Ci minus Cj, the two-sided geometric product with this in between. And of course, that has the advantage of it doesn't change the order of the vector. If you put a bivector, it will preserve a bivector and so on. Whereas if you use one-sided transformations, then you don't get that nice property. Well, here I'm just deriving Heron's formula by instead of defining these inner products equal to 1/2, I'm defining it equal to the length. So C2 plus C3 squared gives you the length of the side, the distance C2 minus C3. Okay, that's row 1. And the interesting thing is when you do that, then you get 2s. If you take C1 plus C2 plus C3 squared, you get that as a sum of 1/2 the sum of the perimeter of the triangle. Okay, so again, this is row 3, this is row 2, and this is row 1. So it's 1/2 the sum of all these three sides. Row 1 plus row 2 is the perimeter of this triangle here. Okay, so it's 1/2. So you see 2 times so S is the perimeter of the triangle. So 2S then is exactly equal to the square of C1 plus C2 plus C3 squared. Okay, and then if you just take C3 minus C1 and you square that out, you get this expression. And that is exactly what Heron's formula is. So you have a new way of looking at Heron's formula. And what Dr. Havel has done is he's generalized this formula to the tetrahedron and higher dimensional simplices, actually generalizing Heron's formula to the volume of any simplex in any number of dimensions. So we were thinking about seeing how, well, in fact, he's generalized some of this already to higher dimensional cases using this so-called null cone geometry to generalize Heron's formula, not only for a triangle, but for a tetrahedron and higher dimensional simplices then. So, it's interesting that you get Euclidean geometry in terms of using this geometric algebra 1, 2, which is isomorphic to the Euclidean geometric algebra G3. So there's all kinds of things going on like that I think should be studied using, so I try to do it with the 4 vectors, tetrahedron on the null cone. But there is some problems with that, so I'm not going to spend time on that. But we can calculate this thing, and you can do the same thing. You'll see, defining again the length, one would hope that it would work out, but there are problems with that, which I won't try to talk about here. That need to be looked at in more detail. Okay, now let me talk in more detail about this global duality versus local duality. So I hope this will clarify Dr. Page's. Okay, so let's consider this. First of all, let's try to make clear this idea of global duality versus what I call local duality. So let's start with a 2 to the n dimensional Grossman algebra. And okay, so we take n null vectors, a1 up to an, which all have square 0, and which all anti-commute. So it's just 2 Grossman algebras generated by n null vectors, a1 up to an. Well, so that generates a Grossman algebra of 2 to the n dimensions, which I call Gn. Okay, and I'm doing the same thing. Okay, let's put a 1 there instead because of our previous comment. So we have 1, then we have the null vectors. We have 2 vectors, k vectors up to n vectors. So that's 2 to the n dimensional Grossman algebra. Okay, but now I take a second Grossman algebra generated by b's. So again, all these b's have square 0, and they anti-commute with each other. So we call this Grossman algebra Gn, generated by n null vectors, all anti-commutative. And now we're taking a second Grossman algebra, b1 up to bn, all having square 0 here. Bi bj equal to minus bj.
Excuse me, Professor Garret. Are you in the same space, the 2 Grossman algebras?
Well, they're separate. I'm saying they're in this, what I call that general null vector algebra N. Okay, you can think about it as being subalgebras.
Okay, then you are taking subspace of.
Yeah, but right now, that's right. You can think about all these geometric algebras as being in n comma 2n, a subalgebra of that more general algebra. That's right. So I take all those null vectors and put them all in the same algebra, saying that the rules are the same as matrix algebra, but they're all generated by null vectors. The most basic quantity are the null vectors, in this case, a1 up to an, generating 1 Grossman algebra, and b1 up to bn. I haven't said anything about the relationship between those 2 Grossman algebras. They're just 2 Grossman algebras, 2 to the n dimensional Grossman algebras generated by the first one, a1 up to an null vectors, which all have square 0, and anti-commute. That's what I call the Grossman algebra Gn. Well, you separate it into k vectors, and you have, put 1 here because it is over the real numbers. And then we have G1N, that's the vectors, null vectors, null bivectors, null k vectors up to null, well, a pseudo-scalar element, which is the product of all those null, which is also null because they all anti-commute. And now I'm calling the second, take a separate set of null vectors. I haven't said anything about the relationship between the A's and the B's. So we're just taking a second Grossman algebra, all having square 0, anti-commutative. So again, that's a 2 to the n dimensional geometric algebra consisting of vectors, bivectors, and so on. Okay, now I'm saying I'm calling them globally dual if they satisfy this relationship. Okay, we say that 2ai dot bj is equal to ai bj plus bj ai, and that's just the delta function. So it's 0 when I is not equal to j, and equal to 1 when a is equal to j. But now I claim this is where a metric is being defined. And when I put that metric in here by defining the relationship, saying what the inner product of ai dot bj is, and you see what it's saying here is when I is not equal to j, a1 dot b2 is equal to 0. So all the for I not equal to j, the ai's and the bj's anti-commute, okay? But when I is equal to j, then the inner product is equal to a1 dot b1 is equal to 1/2. Okay, and I say that defines the geometric, that's the metric now, and that defines what has been called the mother geometric algebra. So it's a 2 to the 2n dimensional geometric algebra with signature n comma n. So it has n vectors which have square +1, n vectors which have square -1, has neutral signature. So p comma q is equal to n, and it's isomorphic to the real matrix algebra 2 to the n cross 2 to the n dimensions. Okay, so that's the definition of what I call global duality. It satisfies this property. Okay, so we have two Grossman algebras. They're globally dual if they satisfy this basic relationship, and that's the equivalent to saying that that's the geometric that's the metric now in the algebra. It's of neutral signature. That's saying that p comma q is equal to n comma n, and it's isomorphic to the real 2 to the n cross 2 to the n matrices. Okay, now what do I mean by local duality? With local duality, I say we take only n null vectors, C1 up to Cn, which all have square 0, and they all anti-commute. So that's like one of those algebras that we chose previously. And okay, and I define the Grossman algebra. First of all, this is the Grossman algebra. So in this case, they're all anti-commutative. I haven't put a metric on the algebra yet. I say they all, so they just span it. It's just like either the A's or the B's. It's just another geometric algebra, all in this, what I call capital N, the set of all null vectors, and taking the products and so on. Only saying that they satisfy the usual rules of matrix multiplication. Okay, so we have a single geometric algebra, the Grossman algebra, generated by n null vectors. And okay, so it has 0. Okay, put a 1 there again. Then we have the null vectors, null bivectors, null k vectors. So there's no geometric algebra yet. It's just that one single Grossman algebra. But now I define what I mean by locally self-dual. So take any two of those vectors, and you say that 2 times c, now we're defining an inner product between any two of the ci and cj. So 2ci dot cj equal to ci cj plus cj ci. That's the symmetric part. I've already said what the anti-symmetric part is. It's the anti-symmetric part that's defining the Grossman algebra. And now the symmetric part, I'm
Sorry,
identifying.
this means that when you say the symmetric parts, are you speaking about only one element, or are you speaking about the set of elements that
No, I'm saying
have
I'm thinking
symmetric
about.
parts?
I'm thinking. No. I'm thinking about the symmetric part of the multiplication of null vectors. That's the thing. If you look at the definition of the bivector product, it becomes anti-symmetric. But that's the thing. You're mixing the idea of symmetric in any support in higher dimensional spaces. It changes. That probably leads to much of the confusion here, because when I say the symmetric part, I'm talking about the symmetric part of the multiplication of vectors. But the symmetric part, when you multiply a vector times a bivector, then actually the symmetric part looks like it's anti-symmetric, but it is. But that's what's probably confusing about it. Okay, so you see here, I'm defining the self-duality, defining the inner product of two null vectors, Ci and Cj. And I'm saying that that's equal to 1 minus delta ij. So you can see when I is equal to j, then we get 0. Well, that's because we said that the Ci squared is equal to 0. So when I is equal to j, that's just saying that the inner product of Ci with itself is 0. Well, that's the same thing. The wedge product of Ci wedge Ci is 0 because of the same
But
vector.
if we switch here I and j, we have the same, because we have by definition the symmetric part here.
That's right. That's defining this. We're saying before I only define when I define the geometric algebra, I only define the anti-symmetric part. You see, these things are all anti-symmetric. A1 times A2 is minus A2 times A1.
The elements are antisymmetric here.
That's right. And that's the same with the C's. I define them all to be anti-symmetric here. C1 wedge C2 is equal to minus C2 wedge C1. Now, C1 wedge C3, they're all anti-symmetric, okay? That's what we're saying right here.
Mm-hmm.
But the thing is, when you look at the definition of a bivector in geometric algebra, that's where you have to change signs because remember, two vectors anti-commute, but if you take C1 times C2 times C3, C1 will commute with C1 wedge C2, okay?
But here in the equation that is in this definition of local duality, you are using the dot product.
Well, I'm defining the dot product. I'm defining it to be the symmetric part.
And then this is symmetric.
Yeah, that's right. It's symmetric. Well, when I is not equal to j, when I is equal to j, then it's 0, right? Because set I equal to j, then you get 1 minus 1, so it's 0 then. So it doesn't contradict.
Okay, this is not contradicted with the definition of the algebra.
That's right. The anti-symmetric part for vectors is exactly the anti-symmetric product. We can see when I is equal to j, then we get 1 minus 1. So Ci is equal to Ci Cj is equal to minus Cj Ci, which is exactly what we said. What we said here. Okay, Ci Cj is equal to minus C. It doesn't contradict that at all. Now, if you have three vectors times Ck, well, of course, Ck is going to anti-commute with Ci, anti-commute with Cj. So Ck.
There's something strange going on, because you wrote Ci Cj plus Cj Ci. Isn't that necessarily 0?
Well, I say it's equal to 1 minus delta ij.
But you said up above that Cij is equal to minus CJI.
Mhm.
That's right. But in this case, well, if you want CI dot CK, then you have to replace J by K here.
Okay,
So it's,
well then, what do you mean by Cij versus C sub I times C sub j?
okay, well, CI times CJ is equal to CI dot CJ plus CI wedge C. So that's right.
No,
Uh-huh.
no, just above. Like,
Okay, so at this point, at this level, we only have the outer product. I'm just defining the outer product of n null vectors. So I say they're null vectors because they have square zero. And I'm saying that they're anti-commutative. So distinct elements are anti-commutative here. And that doesn't contradict, it doesn't contradict this statement here, because when I is not equal to J, then we get zero, which is exactly what we have here. So there's no contradiction.
so C
But
sub ij is not equal to C sub I times C sub j.
Well, if I is equal to J, then you get CI squared, which is zero, right? Well, right here, let I equal to J, you get CI squared plus,
But can we replace C sub I times C sub j with C sub ij?
well, yeah, if you have three of these things, C1 times C2 times C3, then if you want to I times K, I'm saying for any IJ, it satisfies this same rule. So if J is not equal to, if I is not equal to K, then it'll be again IK. So if you take three of these things, then, it's the same, it's still zero. I think what's confusing is when you look at a product of three of them, C1 times C2 times C3. Now, okay, but now you have the inner and the outer product. So C1 times C2 is equal to C1 dot C2 plus C1 wedge C2 times C3. So now you have to look at more detail of the geometric product then, but you can see C1 wedge C2 wedge CK, C1 wedge C2 wedge CK is equal to CK wedge. It'll anti-commute with CI times CJ. So, the wedge product of a vector with a bivector will symmetrically commute with that. So C1 wedge C2 wedge C3 is the same thing as C2 wedge C3 wedge C1, because C1 anti-commutes with C2. You have to do two anti-commutivity, and that makes it symmetric then. But I guess I don't know. That seems to be very confusing.
I'm still maybe I'm asking something too elementary, but when you write C subscript I J, right?
Yeah.
Is that not the same as C subscript I times C subscript J?
No, it is the same. It is CI
So
times.
if it is the same, then the second part of your equality has to be zero.
Well,
Because you've just said that Cij is equal to minus Cji.
well, that was before. This is where I'm putting the metric in the algebra. For the Grossman algebra itself,
But just do the substitution. Right? Just substitute C sub I, C sub j with Cij, etc., and then apply the definition, and you have zero. But I don't.
well, okay. Well, now you're thinking. Well, now I'm thinking about Ci times Cj as being Ci dot Cj plus Ci wedge Cj. So I'm saying that actually here at this point, maybe to answer your question, I should say that this is using the wedge
Yes,
product,
yes, you need to use here
the wedge product.
wedge.
Okay, I can see your confusion.
Yes.
That's right. So here I should say, instead of C1 squared, I should say C1 wedge.
But in fact, in fact, you are going to get 0 because for your definition of the the algebra.
Okay. Okay. So I guess I think we should, instead of writing C1 squared, I should say C1 wedge C1, C2 wedge C2.
That part's clear. It's the meaning of Cij. It's the last part.
But you see, look what I did up here with these two geometric algebras. I say A1 up to AN and B1 up to BN. Okay. But now you see I'm putting a metric on it when I say that this when I'm putting
Yes,
this.
but you can do that here because there is no element, A sub 1, B sub J. Like those two, there's nothing in your definition above, right?
Yeah.
That related A and B. But if what you're calling local, there is such a relationship.
Well, let's see. But at this point, I'm only talking about Grossman algebra, so I don't need. I'm just saying that this is a Grossman algebra. But here I'm defining a metric.
Because it's a Grassmann algebra, then that must mean that C sub I, C sub J plus C sub J, C sub I must be equal to 0.
Well, in fact,
Yes.
if you're, I guess I need to make the connection between that when I'm talking about when I'm going to this step here, that's where I'm saying the Grossman algebra is defined by the wedge product, and the symmetric part. Well, it's also because remember in the geometric algebra you have a symmetric part and an anti-symmetric part. Well, the symmetric part is defined by the metric, so that's where I'm putting a metric on it. But there's no metric in the Grossman algebra here, so I don't need to say. But when I go from this step to this is where I'm defining the metric of the algebra by the inner products. There's no inner product here because, well, you can think about the inner product as all being 0. But here I'm imposing a new metric on this Grossman algebra defined by this. So this is a Grossman algebra, no metric, but when I put this definition, that's where I'm putting a metric on. I'm saying the inner product now is identified with the metric of the algebra. That's where I'm getting the geometric product then. I don't see anything wrong with it. Maybe I need to say more about it, but I certainly don't see anything wrong with this. Well, that's what I'm trying to say here. So if I take gn dot gn, I get g1 comma n minus 1. And those are the Lorentz geometric algebras then. And that's the multiplication table.
But in your multiplication table, then you are speaking about the Clifford product.
Well, that's right. When I put that definition, then I'm talking about Clifford algebra then. But before that, I'm talking only about Grossman algebra.
But then the Clifford product is not the same that Cij. It's not. It can be.
Well, that's right. Well, that's right. I'm thinking about at this point, I need the wedge product. Ci times Cj is a symmetric part plus the anti-symmetric part.
Then in the first expression, in the definition of Grassmann algebra, you have the wedge product. And in the definition of local self-duality, you have the Clifford product.
Well, that's right. The local duality.
And then they are different.
Well,
Cij is wedge product.
Well, yeah, but the wedge product is anisymmetric. So
Yes,
when I look at
yes,
C1 squared, well,
because this is Caj equal to minus Cji. And this is correct. Yes, this is wedge product here.
Yeah.
But in the definition, it's no longer wedge product.
Yes.
In the definition, this is some other product.
Well, what is it then?
Okay.
Definition then?
Okay, that's right.
Okay,
It must be Clifford product. Right?
Well, at the top, I'm only talking about Grossman algebra, so there's nothing wrong with that.
In the
But
definition,
now imposing a,
but in the definition,
yeah.
In the definition, you've introduced a new product. When you write C sub I times C sub J, that's a different product.
Well, maybe I should, that's right. Maybe in my definition of the Grossman algebra, I should say for I not equal to J, Ci is equal to minus Cij. We can see if I is equal to J here, you get Ci squared is equal to minus Ci squared. Well, that's 0 is equal to minus 0. So maybe if to fix it in your mind, maybe all I have to say is for I not equal to J, Cij is equal to minus Cji. Would that fix it in your mind? I just say that C1 squared equal to C2 is all equal to 0, okay? But when I is not equal to J, then Cij is equal to minus Cji. So that's okay, right? Anything wrong with that? So all I have to do is add, when I define the Grossman algebra, just say for I not equal to J, Cij is equal to minus Cji. That's all. All I'm saying in the first statement is that they all have square 0. And that doesn't contradict my definition at all then.
No, the first definition, like when you define Grossman algebra, that's clear. There's nothing unusual about that at all. But when you make the definition here of locally self-dual, when you write C sub I times C sub J, it isn't clear what you mean by that. Like you haven't said anywhere.
Okay, but like I say, look at that first line at the top, okay? Just say that for I not equal to J, we define Cij equal to minus Cji. And don't say anything about when I is equal to J. That's
no,
what I
you
say.
Don't have to fix that. You don't have to fix anything there. Nothing is strange about what you wrote. That's perfectly fine. But under the locally self-dual definition, when you write C sub I times C sub J, it isn't clear what the multiplication is. Down, go down. There. No, not that far down. This one, right there. No, right. The first line under where it says definition. Yes.
Yeah, okay.
Now, what is the meaning of C sub I, C sub J? The first term in the sum.
Well, I'm defining.
Not that one. The next term, that one.
This one.
When you write the multiplication between those two elements, what is that multiplication?
Well, you can think about it as the symmetric part and an asymmetric part. Right? You just write
Of
it.
some
Ci
new
times
multiplication,
Cj is
right?
equal to 1/2 Ci Cj plus Cj Ci plus 1/2 Ci Cj Cj minus Cj Ci. You can always write any product as a symmetric part and an antisymmetric part. So all I'm saying here, I identify the antisymmetric part as being the Grossman algebra. And here I haven't said anything about the symmetric part, but now I'm defining the symmetric part as an inner product. That's where we get the geometric algebra then.
But because G sub n is a Grassmann algebra, when you write that multiplication, it's sort of implicit that that multiplication is wedge. Because you said that G sub n is a Grassmann algebra.
Well,
And
that's
so when
right. At
you
this
write,
point, I'm not talking about a Clifford algebra. I'm talking only about a Grossman algebra.
but then C sub I, C sub j, C sub plus C sub j, C sub I has to be equal to 0, right?
Well, when I is
that-
not equal to j.
Nothing to do with that. No, not at all. Just that sum, just the sum that you wrote. If that multiplication is Grassmann multiplication, then that sum is 0.
Well, yeah. Well, yeah, yeah. So you're saying that this definition doesn't mean anything, or what are you trying to tell me?
No. Well, I'm saying that you have to introduce something else, some new multiplication. So you have to make sure that when you write C sub I, C sub j, it means something different than Grassmann multiplication.
The antisymmetric part can be identified with the Grossman algebra. That's all I'm saying. That's what we do with geometric algebra. We identify
But
the
the
antisymmetric product as
but-
being
no,
bivectors, trivectors, and so on.
Sure, but one more thing is just that if you ask what is the symmetric part of a Grassmann algebra, the answer is 0.
Yes.
Well, that's right. So if you ask what the symmetric part of a Clifford algebra, you get the metric of the space. Well,
True.
but actually that only works for vectors, the symmetric part of the product of two vectors. You write as a symmetric part and an antisymmetric part. You identify the antisymmetric part as defining the Grossman part of the algebra.
But let's suppose we introduced a new symbol that meant Clifford multiplication. So I don't know, write a star or something, right? So then you would have to write C sub I star C sub j, because, and then the question is, what is this star, right? Like what, and so now in this definition, you'd be defining what star is, I guess.
Yeah, I just don't see the problem that you're talking about. Maybe you like to. Yeah, I don't see a problem. That's the whole problem. I don't see a problem with this.
But it's just a question of what is the multiplication.
Well, like I say, in a geometric algebra, you take the product of two vectors and you write it as a symmetric part, which is defined by the metric of the space, and an antisymmetric part, which defines the Grossman. Well, when you get the higher dimensional space, you need the anti-commutativity to define what you mean by a bivector. And that's why we have the discussion, does bivectors exist for characteristics?
But you just said, you've said just right above that C sub I is an element of a Grassmann algebra.
Okay, and when I say now we're going to put additional structure on that Grossman algebra by
You're going
defining
to,
this
but you're going
definition.
to, by structure, you mean you're going to define a new multiplication over and above the Grassmann algebra. You're going to define an additional
I'm looking at the
multiplication.
Grossman algebra as only defining the anti-symmetric part. So maybe I'm thinking about a Grossman algebra in a different way than you're thinking. A Grossman algebra just says vectors anti-commute.
But okay, if you completely removed the second part of the equality, if you completely just wiped that out and you only said 2ci dot c sub j is equal to 1 minus delta ij, then I don't have any question. Like, then it's clear that you're defining what you mean by dot.
Okay. Okay.
Except that Cij no longer, like, yeah, basically you're just defining what you mean by dot. You've introduced a new multiplication. But
Okay.
in addition to that, now you're introducing yet another multiplication implicitly that is what you mean when you write C sub I times C sub j. And you're going to presumably define that as the sum of the antisymmetric part
Okay.
and the
I
symmetric
just
part.
mentioned when looking at this, 50 years ago as a graduate student, that's the way we would introduce geometric algebra. We'd take an inner product, define an inner product separately, and define the outer product separately, and then we put the two products together to get the geometric algebra. That's exactly what we would do. But later on, you don't go through all these details. It's just like multiplication. You define a more general multiplication as take two vectors. You can write it as a symmetric product and an anti-symmetric product. You put them together. That's when you get the geometric product. And then you have to prove all the other stuff that you want to do with it. But you can do that if you want to. But like I say,
It just is very confusing to me to not say what the multiplication is. Like, or maybe it's better that to say that definition is defining two multiplications.
Okay,
at the
well,
same
let's
time.
let's say if we could clarify that. Okay, so let's leave out that the middle CI CJ plus CJ CI and just leave the inner product. Okay, then we would have to say what would we have to do with? We have to say that CI CJ is equal to CI wedge CJ. Okay, and then we have to put the two
Plus,
CI dot CJ plus CI wedge CJ together by doing that. And then we just do the usual stuff then. But there's no problem with it. It's just, you can do that. You can define, study all the properties of the symmetric or the inner product separately, the way they do in vector analysis. You study its it's a symmetric product, CI dot A dot B is equal to B dot A, and go through all those things. And then you take the anti-symmetric part and you study its properties. And then you say you can put them together. And that's when you get the geometric algebra.
I think that the problem is that the elements of the Grassmann algebra are not vectors.
Well, they're generated by vectors.
Are not vectors, and then we can't define a dot product here.
Yeah, generally, a Grossman algebra is generated by vectors. You agree with that, right? So I'm just saying I consider a Grossman algebra generated by null.
No, because your definition is that the products in the algebra, when the index is the same, is 0. and when the index are different, are antisymmetric.
That's right. That's right. That's all.
Then
All we're
there are not symmetric parts here.
Yeah, that's right. When we define
And there are not
you can think about that as being the
products.
antisymmetric. The Grossman algebra is defined by the antisymmetric part. But what's important is your definition of a vector. Before you have the definition of a vector, you can't have a bivector and so on.
Yes, but here in the definition of your algebra, there are not vectors.
Well, in the definition of a Grossman algebra, I start with null vectors to generate the n-dimensional Grossman algebra. We start with, and I say that a null vector generates a direction. It's the abstract definition of a ray, a straight line. So that's vectors, Grossman vectors that define a direction, a unique direction in space, well, or n-dimensional space, or whatever you want. So, but they have no metric. That's all I'm saying. That we're only defining the antisymmetric. Okay, then you take the antisymmetric product. That defines the Grossman algebra. That's the wedge product. I didn't say that here, but of course that's what I want to do. And of course, I put the metric in at this stage right here. So I consider the most fundamental idea is that of direction represented by a null vector with no length or negative, square negative zero or square, it's all square zero. So, okay, maybe something needs to be said more about, well, like I say, when I first introduced to geometric algebra, that's right. We defined the dot product, studied all its properties. It's associative and, well, of course, the vector cross product is not, that's the whole idea. And with geometric algebra, you put the dot product and the antisymmetric part together, and that's a much more powerful structure than just considering that's Gibbs Heaviside. That's of course what we've been doing the last 150 years now. 130 years since Gibbs, and of course that's what people think in terms of again. But okay, so that's right. That's why you're thinking about inner product is okay. You have to study the inner product. That's the way they introduce inner product separately. Study its properties. It's linear and whatever, all the other properties, and then you study the outer product. And then you put them together, and then you get the Grossman, and you get the Clifford algebra. But still, it's not universally recognized. People, well, anyway.
Well, I think for me, it's mostly, I think it's a notational issue because you wrote G sub n. So G sub n is a Grassmann algebra, and so by definition, its inner product is zero. That's just what we mean by Grassmann algebra. So it's much
inner product,
but it'd be much better not to say G sub n is locally self-dual, because G sub n can't be locally self-dual, but something like G hat sub n. You're defining some new algebra. It's not the Grassmann algebra, it's some new algebra. And that new algebra is self-dual in the sense you just wrote. That can't be that multiplication can't be within G sub n. It has to be within some new algebra.
Well, I just don't quite see with this definition here, 1 minus delta ij. If I is not equal to j, then it's
nothing to do with that at all. Nothing wrong with that. Nothing at all.
Okay.
It's just that dot is not something defined in the Grassmann algebra. And nor is the multiplication Ci times Cj is also not defined in the Grassmann algebra.
Okay, but you understand, I want a general product. I don't want to define two products, a wedge product and a dot. I want it just one product,
Yeah,
which is
so
a
then-
geometric product.
I understand that. So that's why I'm saying when you wrote G sub n, it's not, you don't mean the Grassmann algebra, you mean some other algebra with a
So
new
what do you want to call it?
multiplication.
What do you want to call that?
G hat or G,
Well, yeah,
so, and then it's going to turn out that G hat is a Clifford algebra.
okay, well, that's right. So you have to go through what, 100 more pages of stuff to do that?
No, just be careful with the notation. So just so the notation makes it clear that at this point, you're no longer talking about the Grassmann algebra. You're talking about, you
Well,
consider,
about putting a metric on that Grossman algebra. That's what I want to talk about. But you don't want to call it a Grossman algebra. Okay, so what are you going to
not
call it?
anymore, not once you do that. Like as
Well,
soon
why?
as you
It
add
doesn't
it,
really contradict anything. It doesn't contradict what we did before. You know, we still have the Grossman structure, the outer product. Well, I'm going to talk about this in Tallahassee next. I guess I'm going to have the same problem with people. I don't think Clifford algebra is recognized. That's the whole problem, really. They still want to talk about exterior products as they just don't see a general geometric, but they do accept the matrix product. Somehow the matrix product, you don't question that, right? Multiplying a column times a row and all this stuff, that's accepted, right? There's no problem with that, right? And this is consistent with that. I show you how to, it's isomorphic to the matrix algebra. What we're talking about is matrices as being coordinates of these geometric numbers. That's all we're doing. So there's, I just don't see they're just making things much more complicated than they need to be.
No, well, maybe it's it's still terminological issue for me, because when I say algebra, I really am focusing on what is the multiplication in that algebra. Like, so I wanted to say an algebra comes from a vector space abstractly. There's a vector space, so that means we have a bunch of elements that obey the axioms of vector space. And then over and above that, we define a multiplication. We just say, okay, there's now a multiplication on top of that structure. And when we do that, by defining that multiplication, we have defined the algebra. As soon as we define a multiplication, we've said what the algebra is, right?
Yeah.
So it's very conventional to think that we're equating the algebra with that multiplication. Like there isn't anything more to the algebra other than just define what you mean by multiplication. As long as the elements.
I agree that a dot product is different than a wedge product. There's no question about that.
So that means as soon as you do that, you're in a new algebra.
Well, like I say, the Egyptians only wanted to add unit fractions. They had a hard time going beyond unit fractions. But when you get the definition of a real number, you simplify your concepts, the way you think about it, and it becomes very natural. Like I say, geometric algebra is no different than matrix multiplication. They're completely, we're characterizing matrix algebras by properties of anti-commutativity and, well, a metric and the definition of a metric. That's what a matrix algebra is. Well, of course, people say that matrices don't have a metric, but somehow, like I say, history of mathematics is interesting because you can see that the trouble that people had with even the concept of a zero, where it wasn't accepted, much less in a so-called imaginary number. All these things are just conceptual problems that I think people have when they look at Clifford algebra. They still don't somehow. Well, I guess that's Gibbs's fault. He's the one that insisted upon a cross product. Well, that was before Einstein, so you can forgive him for that. But the geometric product is really the natural generalization of the usual product of real numbers, for example, and of course, complex numbers and all these higher dimensional octonians and quaternions and so on are, well, you can see people struggled with that when in the 19th century. Hamilton saw it as a great accomplishment when he finally defined the quaternion product. Well, okay, he had to deal with these things you're talking about. Where does he put the inner product and the outer product for quaternion? Well, okay, they invented quaternions. That's what they call quaternions. Well, octonians, of course, is the next step. Well, of course, mathematicians have gone way beyond that now. They have all the generalizations of even those numbers, centians and higher dimensional cases. Anyway, so I can understand what you're saying. Okay, the inner product is different than the outer product. I certainly agree with that. No problem with that. But like I say, I have just two Grossman algebra and I put the metric on it. And I think you can understand what I'm trying to do. But like I say, maybe someone should, maybe you could write a paper about that and try to clarify that, because like I say, it leaves me pretty cold as far as, I don't want to study the inner product separate from the outer product. I want to put it in when I put it in there and not.
But maybe if you change here, instead of Grassmann algebra, you speak about the geometric algebra.
But it's not a geometric algebra until it has a metric. There's no metric if all the squares are zero.
No metric, but you are introducing the dot product.
Not really. Not until I. Well, that's right. That's what they say. Grossman algebra is just to take the dot product equal to zero. So why aren't you satisfied with that? Why do you want to push it further than that? Okay, so Clifford algebra, the Grossman algebra is just taking the dot product of a Clifford algebra equal to zero. And people know that, right?
But how does this differ from just introducing a quadratic form?
Yes.
Mm-hmm. Well, that's what I'm introducing here, exactly. But I'm doing it by saying that the inner product is locally defined by only two of these null vectors, that's all. And that defines the geometric algebra G1 n minus 1. There's no doubt about that. In my original paper, which is being published by this, Advances in Applied Clifford Algebra, this graph stuff, that's where I started talking. I defined those things. I defined the C's in terms of geometric algebra directly. Here, I'm trying to separate these concepts, but you're pointing out problems that I never envisioned because I guess I've just been thinking about it for the last 50 years. Okay, I looked at definition of an inner product, all the different properties of an inner product. Yeah, you have to go through all kinds of stuff, tricks. And then you do the same thing for the outer product and then you stick them together. That's the way they usually introduce. That's the way I was introduced. That's the way Hesney's introduced it as a graduate student, introducing the inner product separately and then the outer product, and then saying, hey, wow, you can put the products together. Okay, but after 50 years, that's kind of worn off. I don't like to do that anymore. Anyway.
Yeah, I don't think I have a problem if I think that I can understand what you wrote. But I'm just worried about the notation or the terminology. Like when you first look at it, it looks like it's self-contradictory. Like it contradicts itself right.
Well, like I say, we're just talking about matrix algebra and isomorphic to matrix algebra. There's no doubt about that. So it just looks bad, but there's nothing wrong with it.
Well, you just have to be clear that the what is the multiplication at each point? Like what does it mean when you write two elements adjacent to each other? Like,
Well, basically, that's right. I'm thinking about a symmetric part and an asymmetric part. We identify the symmetric part with the metric of the geometric algebra, and the anti-symmetric part we identify with the wedge product. Simple as that.
and so it goes back to what I said initially, that C sub I times C sub J is definitely not equal to Cij.
Well, it is before you introduce the inner product. I don't understand why you're saying I can't. We agree on the before the definition, everything's fine, right? But you're saying somehow my definition contradicts the definition of the to the integrand, and that's what I have problems with.
Yeah,
I
it
think
contradicts it because you haven't said what you mean when you write two elements adjacent.
Well, actually, I did. In the beginning of the paper, I say that we assume that all the vectors in N, this capital N, obey the rules of matrix algebra, square matrix algebra. That's where I put the definition in. So that allows me to, that's in my basic assumption, and these null vectors that are generated by null. I think the most basic concept is the concept of a null vector. And that's just a algebraic quantity which has square zero, which you identify with a direction, a vector, the direct array. That's what I think is the most fundamental idea. And I think that's missed. And I think this concept of local duality is important. But how, I can't introduce it the way you want me to, because, I try to do it, but then like I say, the Grossman algebra in my mind, is defined by the anti-symmetric part. But I do start with this concept of a null vector. That's an algebraic quantity. Well, I started with this N, this capital N. That's generated by rays. And they all generated by null vectors, which have square zero. That's the only structure but I'm assuming that it obeys all the rules of matrix multiplication. So, okay, that's the way I get around having to do all this, prove these properties. I'm just saying in the beginning, we take the rules of matrix multiplication of square matrices as fundamental. So we know those rules. And that's the rules that these null vectors satisfy. So how does that, does that make you happy? It doesn't make you happy, though.
Not too happy, but I understand what you mean. But it's because it sort of mixes the representation of the algebra with the algebra. I'm more used to think of Grassmann algebra as defined abstractly in terms of axioms, and it's a little bit disconcerting if I need to assume an underlying representation of that algebra.
Yeah, well, that's right. So I'm defining, I guess, a new concept in mathematics, the concept of a null vector. What is a null vector? It's an algebraic quantity which has square zero, but it's not equal to zero. Well, just like, what is an imaginary number? Well, it's a number which is not a real number, which has square minus one. That's why they called it imaginary. But that's the thing. I think the concept of a null vector is missing in mathematics, and that a null vector with an algebraic quantity which is not equal to zero, which has square zero, is how you should define the fundamental notion of a direction. Should be defined in terms of null vectors, which that's an algebraic quantity which is not equal to zero, whose square is equal to zero. That's a null vector.
Well, I guess Grassmann
obeys all the rules of of, of normal real numbers except for the commutative law. Well, we give up the commutative law.
And
Because-
Grassman would agree with you. I think the whole point of Grassman, like what started out being Grassman algebra, was exactly that sort of point of view, I think. I mean, that's
Well, that's right. As you know, Grossman algebra certainly is fundamental to mathematics, but they don't look upon it. Well, they look upon it as differential forms and all this other stuff, tensor analysis too. And in fact, that's what I'm trying to. This idea of duality, I think, is basic to these ideas as well. Well, but okay, you accept that introducing. Okay, that's what people do. They introduce the geometric algebra GNN, and then they define all the other matrix algebras in terms. Well, they vary the signatures by, well, like I say, by changing a vector, multiplying it by I squared equal to -1 to get all the other signatures. Well, I'm saying you could do the same thing with this local definition here, and then you just change the signature of the algebra to get all the other algebras.
I think that you go back to the definition of global duality here. No, the definition of global duality is more below, I think.
Oh, okay.
Okay, here. Okay, you are saying that G and H are dual globally, huh? And then
they're all in this general algebra, which I call N. Okay, that's
sorry?
all put together.
No, I like to say that when you are making this definition, you are introducing this product that is the Clifford product. And
Yep.
then you are saying that Gn are dual to Hn. Okay, then when you go to local duality, in the way that we can speak about this local duality, you need again the definition of this product. But then in this definition of product, you need to define first the dual of Gn. First, you need to define.
By the way, these definitions are exactly the same for n equal to 2. They're exactly the same, and that's what I talk about.
No, but you are here only speaking of the definition in terms of a formula, but the meaning of this self-duality is that Gn is dual to Gn. And then the dual of Gn is based in this definition of product.
Okay, yeah, by the way, so what's the difference then? You accept global duality for n equal to 2, but global duality and local duality are exactly the same for n equal to 2. So if you have C1 and C2, that's like having A and B. So you accept it for n equal to 2, but you don't want to accept it for n larger than 2, is what you're telling me. So this table is exactly the same table for n equal to 2. You have A, call it A and B. That's like C1 and C2.
Okay, I understand in the definition of global duality that you are in an implicit way defining the product and the concept of global duality.
Yeah, So for n equal to 2,
both at the
but it
same
agrees
time.
with local duality.
Both at the same time. Yes.
You're making two definitions here.
Yes. Yes. Mhm.
Okay, but for n equal to 2, these ideas are exactly the same, as you can see. If you look at global duality and local duality, it's the same definition, really. Oh, where is it now?
Yeah, I think it's okay.
The global duality, think about A1 and B1. Okay, that's like C1 and C2. It's exactly the same definition.
And after you say they are global duals.
That's right. Well, they're agreed when n is equal to 2. It's exactly the same definition. The definition. So why do you accept it in one case but not in the other?
And in your definition of global duality, you implicit define the product AB.
Well, it's the same thing, really.
Yes. Here are what definitions. Are what?
Yeah. So that's the thing. Why is it okay when n is equal to 2, but when n is larger than 2, it's not correct? That's my question.
But it is correct. No one's saying it's not correct. Only that the notation is a bit confusing, at least, right?
But why is it confusing when n is larger than 2 and not equal to 2?
No, it's confusing when you say local dual.
Well, that's because you only need
Because
any two vectors. All the vectors satisfy the same rule. It's really a new way of defining the matrix product, really. It's equivalent to the matrix product.
When it's global, you have an A and a B. But when it's local, you just have a C.
Yeah, but
So
like I say, when n is equal to 2, they're exactly the same. You just call C1 equal to A and C2 equal to B, and that's the same then. The definitions are exactly
but
the
they
same.
but here you have two different algebras. The A's come from
Well,
one
but they're
algebra.
all in that big capital N. They're all in the null vector. Take all the null vectors and you take their products and sums and all that, then you get what I call a universal algebra of null vectors, universal null vector algebra, which I assume satisfy all the rules of usual matrix multiplication for square matrices.
Okay, that's another, yes, okay, that would be more clear. So in both cases, if we say that you're no longer talking about the Grassmann algebra, you're talking about this N. In both cases, when the very next statement is not a statement about Gn, it's a statement about the algebra N.
Yeah, okay, yeah.
So
well, that's why I call it locally. I call it locally because you take any two, Ci and Cj. It doesn't have to be C1 and C2. It could be C100, C150. It doesn't matter what two you take. They all satisfy.
So, okay, here's another way you could make it clear to me. So if you said Gn is locally self-dual in N, if, right? So it's the
I use the word locally because you only need two to define it. That's all.
But it's local in N. It's not, Gn itself is not local, right? Gn is a Grassmann algebra. So but Gn is local.
Okay. Well, that's why I say self-dual. That's right. We in a way in elements.
But it's only self-dual in N, right?
Okay.
It's only it's when you think of Gn as represented in N, then in N, Gn is self-dual.
Okay, maybe I should. Okay, I could. That's right, and that's locally self-dual in the algebra itself.
but it's not self-dual in GN. GN is the Grassmann algebra, so it's not self-dual at all.
That's right.
It
It's
can't be.
in the geometric algebra.
But as a sub-algebra, or as a, if you mapped it into N, then within N, it's self-dual.
Okay, well, yeah.
according to-
Okay, you don't like the word. How would you call it? What would you call it? Well, okay, just say self-dual, or I'm not sure.
No, just emphasize the
Break
fact that
down.
this is about this algebra N, yeah? The N, the big algebra that you said is analogous to matrix algebra.
Oh, okay, then the capital N, yeah.
Capital N, right?
Oh,
Yeah, so,
okay. Okay,
so,
yeah, okay.
so
Yeah,
G sub
I guess
N,
it needs to be developed more. I haven't really developed that N, the capital N very much. That's right. Because I didn't want to have to go through all these. That's what people do, as you know, defining all these associative law, distributive law, and I didn't want to have to do that. That's what, but that's what mathematicians like to do. But it gets old
but
after a while.
but it's okay. I mean, everything makes perfectly good sense as long as it's clear what algebra you're referring to when you multiply two elements together.
Yeah, well, that's right. I'm referring to.
So,
Well,
so you're referring to this algebra capital N. That's, as you said, you assume that all the multiplications are matrix multiplications.
yeah, that's right. So, well, I'm just, like I say, people, they've never. It's really just a new basis for the so-called Lorentz geometric algebras of signature 1, n. It's just a basis of null vectors, vectors which have square zero of the geometric algebra 1, n minus 1. Well, okay, when n is equal to 2, of course, we get G11. When n is equal to 3, we get G12, and then n equal to 4, we get G13. And that's, of course, the Dirac algebra. So it's again, it's just a way of the Dirac matrices are the coordinate matrices for when n is equal to 4. Okay, because then we have 1, 3, and that's the Dirac algebra. Well, that's the thing. That's the thing. You see, I choose a null vector as being the basic idea of a vector. A null vector just characterizes the direction of a ray, one-dimensional space. Could be the real number system or just so I think of a null vector as just characterizing the definition of a direction. And that seems to be different because, well, now you see all these geometric algebras, they're like G12 is isomorphic to G3, but that's again, you're mixing the definition of a null vector. To me is elementary. It should be used to characterize any other thing in matrix algebra, but of course it's not done that way anyway. Then I talked about these are the gamma 0 is the usual Dirac matrix and so on. Observer frame. Okay, so I'm calling that E1. And my terminology is E1. Well, I tried to talk about the Fano plane. That's not complete still. These ideas are not really, I'm not completely happy with my presentation of the Fano plane, so I won't even talk about it right now. But, well, I just talk about various properties of these things here. Well, I think that one of the interesting points is the way the symmetric group becomes involved because it does give you a new representation of the symmetric group, which is very basic. Well, anyway. Well, like I say, that Fano plane, I want to study that more. I haven't really got around to getting started again, but it has an extremely interesting structure. But notice that the orientations of these little smaller triangles is important in the definition, of course, of the so-called octonions. But I think the null vector approach can give more insight into the Fano plane, which is extremely interesting for this notion of triality. One of the interesting features of Lunesto's book was his definition of triality in terms of the Clifford algebras 0, 7, and 0, 8, or 1, 7, and 1, 8. But this one I try to represent in terms of the geometric algebra 1, 6, where I, instead of naming the points on the Fano plane by, well, normally people do it with F1, F2, F3, F4, but I want to name the vertices of the null of the Fano plane with null vectors, C1, C2, C3, up to C6. But I haven't got everything to work out the way it needs to work out. But so I try to introduce a study of the Fano plane, 7.7 lines, 6 small, 6 larger. So this orientation stuff is very important. And of course, the interesting of these null vectors, as I started out these ideas, I started by thinking about in terms of graphs. Well, and then we got into the talking about relationship to category theory, which I don't know. Dr. Cruz, have you been able to do anything more about these ideas with relationship to category theory? For example, could you build category theory with this notion of duality? I don't know what you don't call
Yes,
it.
I was working with this, and I understood how you can change from dots to arrows, for example, and then you have the same representation. And then I was trying to write for these two representations the objects and morphemes that defines the two categories. And then look about how those categories are related.
Sounds interesting.
It is interesting because the 7 rows that are defined here are the lines, but I prefer to speak about the lines in terms of this, for example, using your picture here. One line is E6, E5. This is E6, E5. This is one. No. In this figure, E6 and now E5.
That's here.
Yes.
The composition.
The complete side of this triangle is a line. Another line is E5, E3, and E3, E6. And now the next line is E6, E2.
E6.
Another one is E3, E1, and E5 is E4. Now we have mentioned six lines, and the 7th line is the circular.
That's right.
E1, E2, E4.
Yeah,
And
that's,
then you need here the three vertex, the three dots, E1, E2, E4. Those are the 7 lines.
Or should you say that there are 3 lines, like E1, E4, E4, E2, E2, E1, right?
This is one, you say, you mention 3 lines now.
Yes, they are all within the circle, but they all involve only one composition.
well, of course, any 2 points really defines a line too, as far as that goes.
No, because
Well, as
here
far as
the
multiplication,
definition of the Fano plane
yeah, that's true.
is seven
Points.
vertex and 7 lines.
Yeah. Yeah, the midpoints are different.
And we need to understand the lines in the way that I said. The sides, the 3 sides of the triangle, the
Yeah.
3 meanders of the triangle,
That's
and
right.
the circle.
That's right. That's right.
So why not take two sides, like E6, E3?
It's E6, E3.
Yes, it's a composition of 4 arrows.
No, because I say E3, E6, then I am only taking the lines in one sense only.
A composition of 2. It's the only E3, E6 is the only composition of 2.
And yeah, but I am now speaking not in terms of category theory, but in geometric terms. And then the line E3, E6 is different of the 2 lines E6, E5, E5, E3.
Yeah, the interesting thing, of course, is those lines define this octonian product. Just
Yes,
by going
those
around it.
lines define the octonian product. Yes, yes.
Interesting.
Uh-huh.
Of course, the octonians are the only division algebra other than the Hamilton's quaternions and real numbers. But of course,
Yeah.
we have to give up the associative law.
Mm-hmm. And now you can think in this in terms of category theory.
Okay, that's interesting.
And then if we think in terms of category theory, then we have too much arrows. Because we have a E6, E1, for example. And we have E1, E5, and so on. Then, in terms of category theory, we have different kinds of composition here. And then, if we change this representation of the Fano plane, changing arrows by vertex, then we have a different set of morphemes. And then we need, I need to explore how these 2 categories are related.
Okay, it sounds promising to me. It sounds very interesting.
Yes. I don't finish the analysis. I needed to and wanted to review some definitions about the rings and their representations by modules. Then I made a presentation with the general ideas of these properties of rings in the way that we can find in the properties, the categorical properties of modules, and then relate this with the Grassman and Clifford Algers.
I might just say here, since I'm on this slide here, that I tried to do some basic calculations. For example, I looked at down here C1 minus C7. So think about the E's as being C's now. C1 minus C7. Let's see.
Okay.
C1 minus C7. Okay, so that's like that arrow there times C5. Let's see, C5 minus C1. Okay. And then C7 minus C5, just to see how these things worked out here. And you can see when I do that, well, it comes out pretty interesting, but it doesn't really give me what I wanted to get. Like I say, well, this is really Baez's picture here, John Baez's picture. These E's all represent vectors which have square minus 1. So all these E1 up to E7 all have square minus 1 in any commutativity. So he's getting the Fano plane construction of Octonian products using vectors which have square minus 1, like a double quaternion type ideas. And that's what Lunesto does too. But anyway, I was trying to do it with these null vectors to see how these oriented triangles come involved in the definition of the Octonian product. But I'm not really finished with it, so but I do calculate these things just to try to get some understanding how maybe you can use. Like I say, basically, this duality stuff came up with graph theory, and this is, of course, a very interesting graph which has all kinds of powerful interpretations as far as applications are concerned. The Fano plane, which is very interesting. So, seemed like a natural way, but it looks like with category theory, you can even go further. Maybe then it would be interesting. We could tie it all together somehow too.
Jesus, would you have the possibility to make some introduction to this category theory, say in 3 weeks?
Yes. I think in 3 weeks I can make an presentation of this.
That sounds interesting to me also, very.
But you say that I can say something now? No.
Well, I think the time is
yes, I think
getting late, so I think it's better to wait until 3 weeks in our next meeting. Perhaps you will have an opportunity to extend some of the slides. I know you showed a few related slides. I'm thinking the last meeting or the meeting before, but still, it would be good if you could sort of put the what we need as a background to category theory, like in order to make the constructions.
I am going to present some ideas about the category of modules.
Mhm.
And then the principal concepts of category that I am using there are functors, covariant functors, contravariant functors related with duality, and then with adjunctions.
Mhm. Some of these ideas are quite advanced ideas in category theory, so maybe it's good to start with examples.
General ideas.
Well, examples.
Oh, okay.
So that it's, of course, category theory is usually introduced in a very abstract way. So it's not always clear the application. So sometimes people call category theory just abstract nonsense, right? Because there's no clear um, application, and the people who study category theory often emphasize this abstractness. But what you're suggesting here is something a little deeper, I think, is to say that we can use these abstract tools and apply them to concepts like Fano plane, or even um, like apply them to concepts of representations of algebras in the sense that Dr. Sobczyk is doing,
Yeah.
and to, I think, to give that categorical sort of description is important, but not to give the idea that it's necessarily so abstract, but rather just that it provides the formal language in which to frame to make definitions that are the definitions according to a formal structure. It's sort of, maybe just to relate to the difficulty that I had today was I felt a little bit lost in that definition because I was lost as to what multiplication was involved.
Yeah.
So that having the formal structure of category theory would help, I think, to avoid that complication, to that uncertainty.
Yes, the idea is that I was working trying to finally arrive to the categorical definition of Clifford algebra and Grassmann algebra. There are some works about this published yet. I remember now Laver, for example, speaking about Grassmann algebras and something like this. I think that are too much interesting. And then I am going to try to include some of these ideas in the
I think
presentation.
that would be very good. I like the work of Laver. He was the one who introduced the idea of category theory as foundations, as basically to replace what you mean by set theory with something founded on category theory, to avoid all of the older problems of the sort of formal application of concepts. By focusing on this notion of the morphisms of the arrows, right? Rather than focusing on the elements, like the objects, right? So category theory is focused on the relationship between things, not the things themselves. And so that we only get to understand the things themselves by all their relationships with
Yeah, I'd like to understand better how the concept of a null vector plays in category theory.
Mm.
A null vector really is just an arrow. It's just a direction. I see a null vector as abstracting the concept of a direction. So, and this, somehow I think there is something new in this idea of you don't like the name local duality, but I'm just using local because it involves only two vectors at any two vectors. So it is a local property of two vectors. How I define the so-called local duality. That's why I call it local, because it's just two vectors involved, and that really sufficient to define all of Clifford algebras in terms of these Lorentz geometric algebras, rather than the usual, these mother geometric algebras of neutral signatures where you need two Grossman algebras. You only need one Grossman algebra to define these Lorentz geometric algebras, which might be called a father geometric algebra if you want to use that terminology. But yeah, I like Grossman. I think he's the most important. As you know, he was very frustrated that his ideas were not well accepted during his, I guess toward the end of his life they became accepted. But Grossman algebra has been employed in differential forms in all kinds of different ways, but there's quite a big body of research around Grossman algebras as well, of course.
Yeah.
Okay, well, I think we should say that's the end of our seminar today. And I look forward to seeing you again in 3 weeks, and we'll focus more on category theory at the time. And Brian, you've been very quiet. Do you have any comments?
No, I just have been listening the big discussion there and trying to follow up. I'm in agree with Professor Page that sometimes the way we explain things for us, maybe it's really simple, but for others could be a little more complicated. But I think it's good. So we are going to move to category theory, which is more familiar to me. So I hope it would be easier this time.
It's the first time I've heard someone say category theory is easier. But that's good.
It's because when I was attending to the seminars with Professor Jesus and Professor Osiewicz, it was like the main core of everything. So you need to like start to understand some things. So for me, at least, certain stuff about category theory is really complex, and also like the meaning. I think it's really profound. So in that part, it could be really sketchy sometimes and confusing. But in the application part, I think it's easier when you start to see how things connect. So
That's a good point. Okay, well, we'll see everyone then in 3 weeks.
Okay. Bye.
bye.
Bye
Thanks
for
a
now.
lot.
Bye.